Okay, so welcome back, everybody. So at the end of lecture last time, I had started discussing. So we've discussed singular points earlier in the semester, but now is the time when they're going to become like front and center, basically. And so I started the discussion of isolated singular points. So, what is the notion of an isolated singular point? So recall that a point z naught is called a singular point. So z naught is called a singular point of a function f if f fails to be analytic at z naught. Okay, if it fails to be analytic at z naught, but it is analytic at some point in every neighborhood of z naught. Or analytic, sorry, not at every point, at some point in every neighborhood. Okay, so that's a big distinction. So it's analytic at some point in every neighborhood. Okay, so that's the idea of a singular point. What makes a singular point isolated? Right. Well, a singular point z naught is said to be isolated okay, if, in addition to actually being a singular point, there's a deleted neighborhood throughout which f is analytic. So it's a deleted neighborhood centered at z naught. If there is a deleted neighborhood of z naught, okay, of some radius epsilon, throughout which f is analytic. Okay, this is the definition. And so the singular point is isolated if there does exist some neighborhood of z naught for which f is analytic at every single point except z naught. Okay, and so the idea here then is in picture, I have some f and it is not analytic at z naught, so I have a hole at z naught. Okay, because z naught is a singular point, it is analytic at some point in any neighborhood of z naught. So any neighborhood of z naught that I draw, f is analytic at some point in that neighborhood. But this singular point is isolated if there exists a deleted neighborhood of some radius epsilon. So we'll say that it looks like that. So there it is. Okay, and on this deleted neighborhood, f is analytic everywhere. So it's analytic everywhere in this deleted neighborhood. This deleted neighborhood does not, of course, include z naught because z naught is a singular point of f, so it can't be analytic there by definition. Okay, but it's analytic everywhere else on that neighborhood. Okay, so this is the notion of isolated singular point. Okay, and this is going to be a central notion for us. This is going to be something that is very important going forward. It's very important that we be dealing with isolated singular points. So I did a couple of examples illustrating what an isolated singular point looked like, right, specifically. So here's first example that we did. If my function f is z plus 1 over z cubed times z squared plus 1, okay, then just looking at this thing, this is a rational function, so the only place this is not analytic, right, by our properties of derivatives, right? We have the quotient rule for derivatives. So the only place that the derivative of this thing, for instance, wouldn't be defined is zeros of the denominator here. Okay, well, the only zeros of the denominator here are, they occur at 0 and plus or minus I, right? And so these are singularities of f. To see that they are isolated singularities of f, I draw this picture. Here are the singularities, right? So here's I, here's minus I, and here's 0. Okay. But we know that this f is analytic absolutely everywhere else. So I picked 3 neighborhoods, right? There's 3 epsilon neighborhoods of I, 0, and minus I. And on those neighborhoods I've indicated f's analytic everywhere except at those points. So there's my isolated singular points. Okay. It's got 3 of them. Okay. An example of something that is slightly nastier is, of course, the principal branch of the log, right? Principal branch of log function. So if I choose the principal branch, the branch cut that I've made is here, right, in red. Okay, then if I look at the origins equals 0, it's a singular point of f, because in any neighborhood that I draw of this point at 0, there is some point at which f is analytic. So, for instance, pick some point here, right, on the positive x-axis. This function's analytic at those points that I've indicated here. Okay, and so at any neighborhood I draw centered at the origin has some point at which f is analytic, and so it's a singular point. That's easy to see. But it's not isolated. And the reason it's not isolated is, again, every neighborhood that I draw about the origin actually contains points on this branch cut, right? And because it does, no deleted neighborhood of z0 that I draw here is going to satisfy f being analytic on that neighborhood, right? Because it's always going to contain this part of the negative x-axis where f is definitely not analytic. And so any deleted neighborhood I draw based at the origin is going to contain those points. And so f's not going to be analytic on any deleted neighborhood of 0. So the singularity of z0 is not isolated, since f is not analytic on any deleted neighborhood of 0. Okay. All right. Okay. Let's do another example. So let's consider the example that is f of z is 1 over sine of pi over z. Okay. What are the singular points? Okay. Well, we could just say the singular points are going to be where the zeros of sine are. And so what's going on here? Well, so singular points occur at, well, when z is equal to 0, that's a singular point. So z is equal to 0. And z is equal to, it's same as for the usual sine function. So z here, or the sine of blah, this needs to be an integer multiple of pi to be 0. So z needs to be 1 over an integer, right? So z needs to be 1 over n, where n is plus or minus 1, plus or minus 2, and so on. Right? Okay. And so here's the singular point. So there's infinitely many singular points. Z equals 0 is one, and z equals 1 over n is another. Okay, so there's infinitely many of these. So question, can a function have infinitely many singular points? The answer is yes. Here they are. Okay, what do these things look like? Well, if I draw this thing here, maybe I'll draw my singular points in red. So z equals 0 is one of them. Right, and z equals 1 over n, so here's, I'll make it here so that you can actually see stuff. And z equals, so when n is 1, there it is. When n is minus 1, there it is. When n is 2, right here it is. And when n is minus 2, looks like that, and so on, right? So, so then this would be like when n is equal to 3. And it would start to do this kind of thing. Right? Okay, so that's what the picture looks like. So there's infinitely many of those. They're going towards z equals 0 here. Okay. Now, note. My first thing to say is that every singular point of the form z equals 1 over n is isolated. How do I notice that? Well, look at, so this thing only has these singular points I've indicated here. So for instance, at this point, to see that it's isolated, I just need to find a neighborhood, a deleted neighborhood of this point, such that f is analytic on that whole deleted neighborhood, right? Well, that's easy. There, right? There's a deleted neighborhood centered at that singular point of f, at which, so f is analytic throughout this whole thing, right? This doesn't contain another singular point. Okay. Similarly, there's a deleted neighborhood for that singular point. We can keep doing this, of course, for any of these. Right? We can keep doing that for any of those. Okay. So every singular point of this form is isolated, but z equals 0 is not isolated. Okay. It is a singular point, but it's not isolated. Why? No matter what deleted neighborhood I draw around z equals 0, it is going to contain some points, some singular points. In fact, it's going to contain infinitely many singular points of this form, right? Just let n be bigger, right? Let n be bigger. So whatever deleted neighborhood you choose here, I can let n be bigger, like bigger and bigger until I am eventually inside that deleted neighborhood that you've chosen for every subsequent big value of n. And so that's it. That does it. Okay. All right. So you're always going to be able to find these singular points inside any given neighborhood, deleted neighborhood of z equals 0. So this is not an example of an isolated singular point. Okay. What is the purpose for coming up with this distinction? Okay. So the important bit, the important point. Okay. If f is analytic everywhere inside a simple closed contour C, except for a finite number of singular points, This is key. Okay. Then all of these singular points must be isolated. Okay. All right. To see a perfect example of this, okay, so to see a perfect example of what it is that's going on here, look at this case, right? And take your simple closed contour to be this thing, right? If this is your simple closed contour C, all right, then this contains a few of these singular points. So for instance, 4 of them, okay, which is finitely many. And so why do those 4 have to be isolated critical points, or singular points? Keep making that slip up. Why do these have to be isolated singular points? Well, here, since there's finitely many of them, basically I can just take the distance of these things to each other, right, and use those, or half of that, as my radius for deleted neighborhoods of those points. So maybe I have to make the radius of these deleted neighborhoods very, very tiny, but I could do that in a systematic way, and I can make them tiny enough so that they are all inside of the contour C if I need, right? Okay. And so this is an example of this working. Notice, right? When would this fail to work? For what kind of curves? What if my contour included z equals 0, right? If z equals 0 was inside of it. Well, now, all of a sudden, right, so I could actually have this contour coming closer and closer and closer to z equals 0 as long as it didn't loop around it, right? But the second that it loops around it, what does that mean? It suddenly contains infinitely many of these singular points, and this thing that I'm trying to say doesn't work anymore. Okay. If you don't believe that this is the case, again, here's a quick picture. Imagine that I have some singular points for a function, but there's finitely many of them, so there we go. There's singular points of function, and there's finitely many of them inside of some curve. See, the idea here is that I can come up with some radius for these deleted neighborhoods, right? If one deleted neighborhood exists, then infinitely many do. You can just keep shrinking the radius. And so eventually I can come up with radii for all of these such that all of them fit inside C and they're isolated, right? Because I can shrink and shrink and shrink. So even if I found one that's inside of C but it contains other, other singular points, I can just make it smaller until it doesn't, right? And that's not an issue here in this picture. Okay, that's what's being said here. So this is important. I'm going to state this. It's actually going to be part of the statement of our big theorem coming up. Okay, but this is something that's good to keep in mind. So if you have simple closed contour that loops around finitely many singular points for some function, then it means that, so if you have an analytic function that's analytic everywhere inside simple closed contour except at finitely many points, those have to be isolated singular points for that function. Okay. One more thing on terminology before we move ahead. Sometimes it makes sense to think about the point at infinity as being an isolated singular point. Okay, so definition of the point at infinity, so isolated singular point at infinity. Okay, so what does that mean? Okay, so if there exists a positive number r, okay, we'll say r sub 1. That's what your textbook uses. So there exists a positive number r sub 1 such that f is analytic, for the annular domain that is where I've excised a radius r sub 1 ball centered at the origin from the plane. Okay, so if f is analytic everywhere up to infinity, right? So that you can consider this a deleted neighborhood of infinity. Then f is said to have an isolated singular point at z naught equals infinity. Okay. I'm not going to talk much about this right now. I'm just going to use it in one particular theorem that I state here in a little bit. Okay. All right. And so that is all that I wanted to say about terminology for now. Okay. So this is the type of singular point that we're going to be concerned with. Now, our idea is to consider a Lorentz series expanded about an isolated singular point for some function f. So suppose z naught is an isolated singular point of f. Okay. Well, since it's an isolated singular point of f, that means that there exists some deleted neighborhood of z naught on which f has this Lorentz series expansion, right? Then there is some positive number r sub 2 such that f is analytic for each z such that this z belongs to the deleted neighborhood of z naught with radius r sub 2, i.e. f has a Lorentz series expansion so remember, Lorentz series expansion for f has the positive power part, so the actual power series part, and a sub n times z minus z naught to the n, plus the bit that contains the negative powers, which is b sub 1 over z minus z naught plus b sub 2 over z minus z naught squared, and so on. Right? A generic term here, of course, looks like b sub n over z minus z naught to the n, but this, of course, keeps going. So there's infinitely many of those that could be non-zero, and this is true on this deleted neighborhood in question. Okay, where the a sub n's and b sub n's can be computed via Lorentz theorem as contour integrals. Okay. In fact, we can actually look at, for instance, the coefficients on the negative powers, right? That's what we're actually going to be interested in here. In fact, we have the following directly from Lorentz theorem. So what does how do I compute these B sub n's? How do I compute generic B sub n in this Lorentz series expansion? Well, directly from the statement of Lorentz theorem, I have these formulas that compute these coefficients. So in fact, a B sub n is computed as 1 over 2 pi I times the contour integral over C of f of z dz over z minus z naught to the m plus 1. Sorry, to the minus m plus 1, because we're using this formulation of it, where f is the function in question, right? And c is some positively oriented simple closed contour around z naught, right? That lies entirely in our deleted neighborhood, right? So where c is any positively oriented simple closed contour, that goes around z, or around z naught, and lies entirely in our deleted neighborhood where this Lorentz series expansion is valid. Okay. Okay. And so, in particular, right, if I let, for instance, n equal 1, right, then what do I get here? Well, in particular, b sub 1 is 1 over 2 pi I times the integral over such a c of what? Well, when n is equal to 1 here, this denominator becomes z minus z naught to the minus 1 plus 1, so that's z minus z naught to the 0, which is just 1 in the denominator here. So this is times the integral of f of z dz. Right? So in particular, the integral over such a contour c of the function in question, f, right, where c is positively oriented simple closed contour that goes around z naught, lies entirely in the deleted neighborhood where this Lorentz series expansion is valid. Okay. Then the integral, the contour integral along such a c that, goes around our isolated singular point, is really just, I can multiply by 2 pi I. This is 2 pi I times b sub 1, the first coefficient on the negative powers in the Lorentz series. And this is just directly from Lorentz theorem. Okay. So this coefficient b sub 1 in the Lorentz series expansion, bring that back for a second. This coefficient b sub 1 in the Lorentz series expansion, this is a special thing. It's a special thing because it shows up directly from this, right, from Lorentz theorem, that this integral of our function in question of such a contour that goes around our isolated singular point can be computed just by multiplying that coefficient by 2 pi I. Okay, so there's something special about this. This encodes a lot of info if what I'm concerned with is integrating the function f that we started with. There's a lot of info encoded here, okay? And so there's a special name for that coefficient. And this is going to be called the residue of f at the singular point z naught. Okay, so definition of residue. So what's the definition of residue? we define b sub 1 in this case to be equal to what's called the residue, okay, of z equals z naught of f of z, and say the residue, okay, of f at the isolated singular point z naught is b sub 1, whatever that b sub 1 is. Okay. All right. So then rewriting this, what do I get? So rewriting, I get the equation, the contour integral of such a contour, along such a contour C of f is actually 2 pi I times the residue of f of z at z equals z naught. Okay. So this is just directly rewriting this equation here, which was fairly obvious using our notation that b sub 1, we're calling that the residue. Okay, so just replacing b sub 1 with this, I get this formula. Okay, which turns out to be our first, like simplest case of what's called the residue theorem that I've hinted at previously. Okay, so this is the first case of it. Okay, now you can see that already we can actually use this to compute some funky integrals. Okay, and so let's look at a couple of examples. So how can I apply this fact? What about doing the contour integral of z squared times sine of 1 over z dz? Right, where c is positively oriented unit circle. Okay. So what is, first of all, if I were to actually look at this thing, right, this integrand. So this integrand is analytic everywhere except at z equals 0. So there's a singular point. Okay. Here is my C, which is positively oriented simple closed contour that goes around that isolated singular point. Even if I didn't know my singular point was isolated, the second that I'm able to draw a simple closed contour surrounding a finite number of singular points, then I know that they have to be isolated singular points. Okay, even if I hadn't thought about it much before then. Okay. All right. And so, since this is the only point, not just inside of C, but in the entire plane, where this integrand is not analytic, I actually have a Lorentz series expansion everywhere. So since z equals 0, z equals 0 is the only singular point of the integrand on the entire complex plane, I have a Lorentz series expansion everywhere on just the punctured plane, right? The deleted plane at z equals 0. So just removing the origin from the complex plane, I have a Lorentz series expansion there. So I have a Lorentz series expansion on the punctured plane, right? Okay, and so whatever this thing is, this integral can be computed as 2 pi I times the residue at z equals 0 of our function f of z, which is the integrand. Right, so this is our f of z. Okay, so let's figure out what this residue actually is, and we're done. Okay. So in order to do this, all I need to do is find the Lorentz series and just find what the first or what b sub 1 is, right? So let's do that. So there's my integrand and the integral that I'm computing. Recall, typically we don't want to have to use Lorentz theorem to actually find what these coefficients are for the Lorentz series because, well, we ultimately want to use a consequence of Lorentz theorem to actually be able to compute these integrals in question. We don't want to compute the integrals. So as usual, the way that we find the Lorentz series is to use something we already know about Lorentz series and Taylor series to do this. And so recall that the power series expansion for sine z is the usual z minus z cubed over 3 factorial plus z to the 5th over 5 factorial and so on. Okay, and this of course is valid everywhere on the entire complex plane. So then what about z squared sine of 1 over z? So here, what's the idea? We replace z just formally with 1 over z, and then we multiply through by z squared. So replacing z with 1 over z, what do I get here? So here I would get 1 over z. Right, so this would be z squared times, and we can do this nicely because of convergence properties that we mentioned previously that make all this nice. So this is z squared times, I'm replacing everything with 1 over z. So this is 1 over z minus 1 over z cubed times 3 factorial plus 1 over z to the 5th times over 5 factorial and so on. So it looks like that. So then here, multiplying through, this is z, right? Z squared times 1 over z, that's z. Here I'm going to get minus 1 over z cubed times this 3 factorial is going to be in the denominator here. So after I multiply through by z squared, I'm going to have a 1 over z there. So this is going to be minus 1 over 3 factorial times 1 over z. I could actually stop there once I figure out that no other term is going to contribute to this term, right? Plus 1 over 5 factorial times 1 over z cubed and so on, right? Continuing on like that. Okay. Thus, where is my b sub 1? If I write this as a Lorentz series, here is my only positive power of z. Thus, b sub 1 is equal to, well, what is that? It's this, right? Okay, so b sub 1 is minus 1 over 3 factorial, i.e. it's minus 1 over 6. Okay. So then what that means then, i.e. rewritten in our new notation, the residue at z equals 0, of f of z, in this case, is minus 1 over 6. And so, using this fact, this is 2 pi I times minus 1 over 6. So this is minus pi I over 3. Okay. All right. So there's a nice example of how to use this fact, okay, to compute this contour integral. All right. Let's do something similar. Okay. So next example, I want to compute the integral over simple closed contour C of e to the 1 over z squared dz, okay, where C is again positively oriented unit circle. Okay. Okay. Well, in order to do this using that fact, this one, in order to use this, I want to compute the residue at relevant isolated singular points. And so looking at the integrand here, what's an issue? Well, 1 over z squared. Note 1 over z squared is analytic everywhere except the origin. Okay. Thus, the same is true of e to the 1 over z squared. Same is true of that composition. Okay. Thus, z equals 0 is an isolated singular point of the integrand that is interior to C. And C is thus a simple closed contour. It's positively oriented that traverses, right, this. It has this isolated singular point inside of it. So I can use this fact, right, that I want to use here, this definition of residue. Okay. So how can I figure out how to compute this? Well, first of all, note that e to the z has a very simple Maclaurin series. Right? I can expand about 0 pretty easily here. So this is 1 plus z over 1 factorial plus z squared over 2 factorial plus z cubed over 3 factorial and so on. Right? That's the Maclaurin series expansion for e. Okay, and of course this is valid everywhere. Okay. So then what's my Lorentz series expansion for e to the 1 over z squared? Well, this becomes 1 plus 1 over 1 factorial times, just plugging in 1 over z squared here, is times 1 over z squared, plus 1 over 2 factorial times 1 over z to the 4th, right, plus 1 over 3 factorial times 1 over z to the 6th, and so on. Okay, and this is valid on the punctured plane. And so this is my Lorentz series expansion, right? I found a thing in the form of a Lorentz series, and due to uniqueness then of Lorentz series expansions, this is it. This has to be it. And so I have to be able to compute these coefficients by all those formulas in Lorentz theorem. Okay. All right, so what do I notice, right? So note b sub 1 here is equal to what? Well, b sub 1, remember, is the coefficient on the, in this case, it would be the 1 over z term. But there's no 1 over z term shown up here, right? So this coefficient is 0. Okay. Thus, the integral along the simple closed contour C of e to the 1 over z squared dz is 2 pi I times the residue of this thing at z equals 0. So this is the residue of, we'll call it f of z here, which is the integrand. This is 0, right? This 2 pi I times 0, which is 0. Okay. So that integral that we wanted to compute is 0. Okay. So a nice example of this, or a nice thing to get from this is that even though, you know, typically if you have the analyticity of an integrand within and on a simple closed contour C, we know that that's a sufficient condition for that integral around C to be 0. But it is not a necessary condition, right? Because here we have a function that is not analytic on the interior of C, and yet its integral is, this contour integral is 0. Right, so this is a key example. All right, so note this is 0, even though e to the 1 over z squared is not analytic in the interior of C. Okay. So our basic example of something that broke the things that we were doing previously when we were first doing Cauchy-Goursat stuff was 1 over z, right? And we found through various other methods that that contour integral, right, of like, say, unit circle, the function 1 over z, is like 2 pi I, right? So it's not 0. But here we have something that also has a singular point at z equals 0. We have an integrand that has a singular point at z equals 0. But actually the contour integral around unit circle is 0. Okay. That's nice to keep in mind as far as a quick way of coming up with in your head, you know, what can possibly happen at points like that. Okay. Let's do another example. Okay. Let's compute the contour integral of 1 over z times z minus 2 to the 4th dz. Okay, where C is the positively oriented circle centered at 2 of radius 1. Okay. Okay. So note the integrand, we'll just call it f of z. So note f of z is analytic everywhere except at z equals 0 and z equals 2. Right. Thus, it has a Lorentz series expansion on the annular domain where I've taken out 0. And it's an open disk of radius 2. So it's a punctured disk centered at 0 of radius 2. So it has a Lorentz series expansion on the following punctured disk. Right, centered at 2 of radius 2. Okay. All right. So then what does our picture look like? So here's my plane. My singular points are here, and here's at 2, we'll say. My circle C is positively oriented, centered at 2 of radius 1. And my Lorentz series expansion is valid on this neighborhood. That punctured neighborhood of 2. Okay. Okay. And so we have everything we need in order to apply this fact here that I'm going to put on screen again. So we have everything we need here. So now we just need to compute this residue. Okay. And so recall, how are we going to do this? So 1 over z, like having, if we can find out, so first of all, if we look at this thing, we know this is our characterization of the geometric series. So the sum from n equals 0 to infinity of z to the n. Right? This is valid whenever the modulus of z is strictly less than 1. We can use this, as we often do, to rewrite this integrand in the following way. So we can actually rewrite this as 1 over z minus 2 to the 4th times 1 over 2 plus z minus 2. Well, look, 2 plus z minus 2 is just actually 1 over z here. So nothing fancy's happening here, just some typical algebraic trickery to make use of what we know about familiar series. Okay, so this is what? Well, let's think about this for a second. Here I can pull a 2 out, right, so that I can make use of the fact, because I need this to be a 1, and this is a 2, so I can factor a 2 out of the denominator here. So this is actually 1 over 2 times z minus 2 to the 4th times 1 over 1, right? Thinking about this as minus, this is 1 minus z minus 2, minus z minus 2 over 2. So I wanted to make this minus minus so that this is actually minus. I could use this fact just directly. Okay. And so what is this? This would be then 1 over 2 times z minus 2 to the 4th times, just directly using this would be the sum from n equals 0 to infinity of, here this is going to be minus z minus 2 over 2 to the n. So I have a minus 1 to the n showing up here. Again, I have 2 to the n in the denominator, and z minus 2 to the n. So let's rewrite this. So this is equal to the sum from n equals 0 to infinity of, I'm going to have minus 1 to the n times 1 over 2 to the n times z minus 2 to the n. And all this is, sorry, let me give myself some room here. So this is, all this is multiplied by 1 over 2 times z minus 2 to the fourth. Okay. So then I have a z minus 2 to the fourth, so this is really z minus 2 to the minus fourth, since this is in the denominator. And I have a 1 over 2 here. So this actually becomes the sum from n equals 0 to infinity of minus 1 to the n times 1 over 2 to the n plus 1 times z minus 2 to the n minus 4. Okay, and this is valid everywhere on that indicated punctured disk, the open punctured disk. Okay. Now, actually, we just need b sub 1 here, right? So note, b sub 1 is the coefficient of the 1 over z minus 2 term. So which term is that here? So I want this to be to the minus first, so I'm picking out the n equals 3 term here. Right? So if I write out what this is, I don't care about what this is, but it's going to eventually get to the n equals 3 term. The n equals 3 term is going to be minus 1 cubed over 2 to the 3 plus 1 times 1 over z minus 2. Right? And then there's some more stuff. Right? Okay. And so what is the residue here, i.e., so b sub 1 is equal to minus 1 to the third over 2 to the fourth, or minus 1/16. Right? This b sub 1 is this coefficient. Okay. And so, using this fact here, our contour integral of 1 over z times z minus 2 to the fourth, okay, dz is equal to 2 pi I times the residue at z equals, this is equals 2 here, right, of f of z, which is the integrand, which is 2 pi I times minus 1 over 16, which is minus pi I over 8. Okay. Alright, so let me know if you have questions about that. Okay. Now, that shows the power of this fact of using residues, right, to compute these contour integrals. Okay, so this illustrates, so those examples showed the power of residues. Remember, residues are really just the n equals minus 1, right, coefficient in the Lorentz series expansion. Right? And it turns out that directly from Lorentz theorem, right, no proof needed, it just fell directly out of Lorentz theorem that we had this fact that we can compute contour integrals of functions in this way. Okay, by computing their residues. That is, by computing that b sub 1 coefficient. Okay. All right. Well, it turns out that we can apply this in a very similar but more general setting to be able to compute contour integrals of functions along contours that encircle multiple isolated singular points. Okay. All right, and so that's exactly what we want to do here. So we now want to do this to do the same thing, except for multiple, but still finite, isolated singular points. Okay. Okay. Right. Okay, recall that if C is positively oriented, simple closed contour, right, surrounding a region on which F is analytic everywhere except except finitely many singular points, then those points are isolated singular points of F. Okay. And in the integral of this F along the contour C, the residue at each such point contributes to the integral. In an obvious way. Okay. This is known as Cauchy's residue theorem. Okay. So this is called Cauchy's residue theorem. By this point, you might notice that almost everything in this course has been named for Cauchy. And the reason for that is because he's basically the guy that single-handedly founded complex analysis. He is the dude. There are a few people working on it too, and there's a few people that did some earlier work on some things. So obviously there have been some other names creep in, but Cauchy is definitely he's the guy when it comes to the foundations of complex analysis, and that's why everything's named after him, because he was the one that discovered all this stuff. Okay, so it's actually kind of redundant to even label all this stuff Cauchy's whatever theorem. He has by this point, I'm pretty sure we've had at least 10 facts named after Cauchy. Okay, and so what is Cauchy's residue theorem? What does it say exactly? Okay, so Cauchy's residue theorem, or more simply known, just the residue theorem. This is the crowning achievement of this course, because this fact is the fact that computationally is going to let you compute all kinds of crazy stuff. My goal is to show you some examples of how you can use this to compute improper integrals of real valued functions. Okay, so this is kind of like the ultimate proof of complex analysis being worth it, I guess, in some sense, right? If you still had some lingering questions of why, what is the point of thinking about all this theory that we came up with, or that we're talking about to discuss functions of a complex variable. Like, what is the point of it if all I care about is real analysis, right? For whatever reason, and I'm just not interested in this stuff. Well, the point is that you can use this stuff. Even if you're someone who only cares maybe about real analysis, you can actually use all of this complex analysis stuff to find and solve problems in real analysis, which is kind of that's like the absolute like finishing touch that shows that this is definitely worthwhile, because it might be like somewhat unexpected that you could do this. Okay, and so what is Cauchy's residue theorem? Okay, so let C be a simple closed contour positively oriented. Okay. If a function f is analytic inside and on C, except for a finite number of singular points. Recall, just from my previous comments, we're in the situation where f has isolated. These points have to be isolated singular points. But if a function f is analytic inside and on C except for a finite number of singular points, and maybe we'll call those singular points z sub k, right, where k goes from 1 to n, so there's n of those things inside C, then the integral over this contour C of f can be computed as 2 pi I times the sum of the residues. So the sum from k equals 1 to n of the residues at the z sub k's. So this on the right is 2 pi I times the sum of the residues. Is the quick way to remember this. Okay. Okay. So, the proof of this is really easy. So it's an amazing theorem, but the proof of it is really easy because we have actually done the legwork. Although I think when we originally did this, rather than actually working out all the details, I think I just gave you a sketch of the proof of this fact and told you to refer to the text for the rest of it. But a fact that we stated earlier in the course allows us to basically prove this immediately. So the proof is the following. Maybe I'll do the proof on the next page and save this as kind of pristine. No, okay, I'll do it here. That's fine. Let's say that the situation I have looks something like this. Okay, so I have a region interior to positively oriented curve C. I have some finite number of z sub 1, z sub 2, z sub 3, and so on, all the way to z sub n. These are my finitely many singular points of f. Well, since there are finitely many of these, I can find some radii, right, of open disks, open punctured disks, I should say, about each of these, such that f is analytic everywhere on these punctured disks about these, so that I can make these, like, in particular, what is it that I'm doing here? I'm doing it so that I can make these neighborhoods small enough so that they don't contain any other isolated or any other singular points, right? And the fact that I can do that means these are isolated, right? So that's why this is important, okay? But once I've done this, I can choose circles, right, of some radii centered at those points. And I can consider positively oriented such circles. So there, make them all positively oriented. So here's C sub 1, here's C sub 2, here's C sub 3, and C sub n. Right, those are all those circles. Okay. All right. Now that I've written out all these circles, well, then I can consider, note, f is analytic at all points on C, on each C sub I, and at all points between, right? When I say between, I mean all points exterior to the C sub i's and interior to C. Right? Exterior to the C sub i's and interior to C. Where have we seen a picture that was strikingly similar to this? When we did our generalized Cauchy-Gorsat to a multi-connected domain. Okay, but remember, we saw a similar setup in our generalization of Cauchy-Gorsat. To multi-connected domains. Right? So we did this right after we talked about simply connected domains. We talk about multiply connected domains. Okay. And basically, we could have the setup in our multiply connected domain that looked like this. By this version of Cauchy-Gorsat, you should go back. I can't remember off the top of my head what number the lecture is, but by this version of Cauchy-Gorsat, we know that in the version that we showed, I believe all of our interior circles were negatively oriented. The exterior one was positively oriented, and so there's a sign difference here in what's stated. But that's exactly what we need. So we know, for instance, that this contour integral over that region could be computed as the contour integral of f over c minus, because they have the same orientation, the sum from k equals 1 to n of the contour integrals over the c sub k's of f of z dz. And this had to be equal to 0, right? So remind yourself, this is the setting. It was so this is our application of Cauchy-Gorsat. So on such a region where f is analytic everywhere in between and on all the circles in question, then what you had was that the contour integral of f over the exterior boundary, right? When these were oriented in the opposite direction, this was plus the sum of the contour integrals over each of these boundary circles C was equal to 0. We change that plus to a minus when these are all negatively oriented, right? They all have the opposite orientation as in the original statement of the theorem. And so this was our version of Cauchy-Goursat to such a domain that looked like this. Okay. All right. But actually, this means that my contour integral of f over the c is equal to the sum from k equals 1 to n of these contour integrals, z sub k f of z dz. But what are those? What are these contour integrals along those circles? Along each circle, well, along each circle encloses a single, each one of these subcircles right inside encloses a single isolated singular point. And so, around each circle, to compute that contour integral, I can use this fact. Now we're in the case that we have a single circle, right, around a single singular point, right? And so I can apply this fact that just immediately came out of Lorentz theorem, that is 2 pi I times the residue at that point. So the integral along c sub 1 is 2 pi I times the residue at z sub 1. This contour integral along c sub 2 is 2 pi I times the residue at z sub 2. This contour integral along c sub 3 is 2 pi I times the residue at z sub 3, and so on. So each of these integrals contributes a 2 pi I times the residue at the singular point enclosed. And so this is literally 2 pi I times the sum from k equals 1 to n of the residue at z sub k of f of z. And that's it. This is the residue theorem. Okay. That is it. All right, let's see an example of how to apply this, and we'll be done for the day, and we'll be ready to spend the remaining 3 lectures going over just all the cool applications of the residue theorem. Okay, so we'll do one example here. All right. So let's consider the following. So here's our example. Let's compute, so let's use this. Let's use the residue theorem to compute the integral over c of 5z minus 2 over z times z minus 1 dz, where c is the positively oriented version of the circle centered at the origin of radius 2. Okay, so note C, right, what does this picture look like? This thing has, what did singular points look like? Singular points at 0 and 1. And here is what C looks like. Right, so here's C, and it's described positively. So here's my singular points. There's 2 of them in there. Okay, and C encircles both of them. Otherwise, this integrand is analytic everywhere in the interior of C. Okay, so these are 2 isolated singularities there, both inside of C. Okay, so I want to find the residues at z equals 0 and z equals 1. So I want to find residues here. So to find the residues, what do? So first of all, as usual, I want to use my favorite Maclaurin series. That gives me an expansion of this thing in terms of geometric series. So this is our usual geometric series. And so this is obviously valid only when modulus of z is strictly less than 1. Okay. Thus, when we consider points on the punctured unit disk centered at the origin, if I look at 5z minus 2 over z times z minus 1, how can I use this to obtain what it is I want? Well, this, I think of this, of course, as 5z minus 2 over z times minus 1 times 1 minus z, which allows me to use that characterization, that Maclaurin series. Okay. And so this allows me to, so now I can divide through by z. So this is like 5 minus 2 over z, right, times minus 1 over 1 minus z. Well, all I have to do is multiply this by minus 1. So this is minus 1 minus z squared, and so on. Okay. And so now all we have to do is pick out where the coefficient of the 1 over z term is, right? And so in this case, right, this is our, if we're calling this z sub 1 and this is z sub 2 here, then our residue at z sub 1 of f of z is what? It's going to be, where do I get the coefficient from 1 over the 1 over z term at? Well, I multiply, so here I'm multiplying through by 5 here. There's nothing but positive powers of z. Here, the only power of z to the minus first here I get is when I multiply minus 2 over z times minus 1. So that's 2 over z. So this is 2. Right? Okay. So that's the first residue. To get the second residue, I can rewrite, note also that if I rewrite this to be expanded about 1 here, the other point, the other singular point, this is 5z minus 2 times z, or over z times z minus 1. So I can rewrite that as 5 times z minus 1. If I do that, this is plus 3 to do this rewriting. And in the denominator here, I'm going to have z minus 1. Okay. And that, then I want to multiply that by 1 over, here I'm shifting z, rewriting z as z plus 1 minus 1. So this is 1 over 1 plus z minus 1. So tricky algebra to do this rewriting. Okay. This is going to take a lot of practice to get used to exactly the algebraic manipulations you have to do to make this work out. Okay, and we'll do a ton of examples of these when we can. Okay, and so rewriting this, dividing through by z minus 1 here, I get 5 plus 3 over z minus 1. Right, so this is 5 plus 3 over z minus 1 times, here I'm just formally substituting this into my expression for the geometric series here. So this is 1 this is 1, so because this is not 1 over 1 minus here, if I wanted to make that minus, this would be 1 minus z minus 1 plus z minus 1 squared minus some stuff. Yeah, there we go. That would do it. Okay. And so when the modulus of z minus 1 is strictly less than 1, in which, so we're in that case, in this, in the setting that we're in. Recall, c is the circular radius 2. Centered at the origin here, so this is fine. Right, this is a good example of showing where exactly those bounds come in here. Okay, and so then how do I find my residue here? Well, my residue when z is equal to z sub 2, which is 1, right? So when z is equal to 1, z here, this is going to be the coefficient on 1 over z minus 1. Where does that come from here in this product? Well, I'm only going to get it from one term. That's 3 over z minus 1 times 1, so it's 3. Okay. And so, using the residue theorem, so by the residue theorem, the contour integral of 5z minus 2 over z times z minus 1 dz along that curve C is 2 pi I times 2 plus 3. So it's 10 pi I. Okay. What does the picture look like that we were actually drawing here? Well, we were doing this we were doing our Lorentz series expanded in neighborhoods that look like that. Okay. Now, this is not actually the only way to handle this. We could actually have done this in another way, algebraically, that would have been very similar, but this is showing you how you can do it exactly in this way. If you notice that you can actually do a partial fraction decomposition of this thing to make it significantly simpler, you could actually do it piece by piece, and it's actually even easier. Okay. So anyway, that's our first application of residue theorem. We will continue on from there. Okay, so you're going to be seeing nothing but this for the next 3 lectures. So anyway, that is it for today. So I will see you all soon.